we've got Newton's law of cooling. We've got an initial temperature. Basically what I've been telling kids is anytime you see a subscript 0, that's normally a starting point for something. But the reason we stop using T so much is because, let's be honest, there's lots of T's in this equation. If we keep using T for everything, it's going to get a little overwhelming. All right, so I am given that I've got an object heated up to 100 degrees Celsius. So if you want, you can think of it like the 3D printer, because that back there is currently running at 195 degrees Celsius. All right, it's heated, and then it's going to be allowed to cool in a room where the temperature in the air is 30 degrees Celsius. All right, so the 100 is my initial temp, and then this is going to be the constant temperature of the surrounding area. All right. Now I know that the object hits 80 degrees Celsius after 5 minutes. So 80 equals, this is where you plug in all of this crap to the formula. E sum K, but it takes 5 minutes. All right, now I need to go through and solve for K. So start combining some crap, move this 30 over, so I've got 50 equals 70 e to the 5k. Divide both sides by 70. Bless you. And I get k equals the natural log of 5 divided by 7 over 5. So what do you get? All right, so negative 0.06. What comes after that 6? So we'll go 7.3. All right, so I'm half done with this problem, because they really want to know when is that temperature going to get down to 50 degrees Celsius. All right, so 50. Now, first and third, we're asking quite a bit, like, okay, do I have to solve it algebraically? No, you don't. But are you going to be able to type that into your calculator fast enough and find the intersection point before you could solve it algebraically? Because if you can't, if you really struggle with the windows, bless you, I would not mess with y1 equals y2 on something like this, especially when you can just solve for it kind of quickly. Subtract the 30, divide by 70. So that gives me 20 equals all that crap, divide by 70. So 2/7 equals all that crap. So T will equal natural log of 2/7 divided by So, what'd you get? Six one? Okay. Not too terrible? Alright. So, what do you notice happens with that temperature as time passes? Where is it going to approach? What should it approach? Yeah, the ambient temperature. So when it comes to cooling and heating, you're just trying to get everything to kind of equal out. So the temperature approaches All right, can I scroll past the ambient temperature part? All right, so this is a lot of writing, I'm sorry. But it's all of the facts you kind of need about logistical functions. Why are you angry? You guys know how there's always a fish tank at the dentist's office, and little kids are just obsessed. Oh, I'm printing two of them at the same time. Now, have you guys actually seen a logistical model? No? So you guys know exponential growth goes up forever and ever and ever and ever. Logistical models look a little something like this. You've got an asymptote here. You've got an asymptote here. This one is your carrying capacity up at the top. Bottom one's typically 0. So let's say you dropped a whole crap ton of bunnies off. That doesn't even look like a 0. You dropped a bunch of bunnies off on an island. What happens? Yeah, they make babies. Yep, exactly. So drop off some bunnies. It starts growing, 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 growing. Eventually, it reaches the point where the island can no longer sustain any additional bunnies. So with a logistic model, it ends up tapping out at that carrying capacity. So what happens is you have too many bunnies and not enough food, and eventually the poor little bunnies start starving, and they die off, and it kind of reaches homeostasis in that environment of this is the max amount of bunnies we can handle. What do you got? With a model, you're more using it to predict what would happen. Like real life, yes, bunnies would go up and then bunnies would tank a bit and then it would kind of stay right around there. You're just trying to predict, like, when will the island reach this many bunnies? All right. Can I scroll past the whole list? Do we need any? We need 5 and 6. All right. Like that. Then we're going to talk fruit flies. And third period's obsession was trying to say fruit flies 5 times fast. ready to start talking about the flies? Alright, so I got some flies. I've got a model for it. The first thing is, what's the carrying capacity? So what is the maximum number of flies my little thing can handle? Yep, it's just the 230. So 230 little flies. Now, part B starts asking about what is the initial population. This is where you're going to have to plug in t equals 0. All right, now what happens to e when it's raised to the 0 power? It becomes 1. So it means I can be a little lazy with what I'm entering into the calculator. Oh, you stupid thing. 230 divided by 1 plus 56.5. All right. You should get a whole number. All right, what'd y'all get? Okay, so I have 4 flies to begin with. All right, part C, what am I going to have to do? Yeah, plug in 5 for t. No, decimal's okay, because remember, this is a model. It's not going to be perfect. So what'd you guys get for number of flies? So after 5 days, I'm getting really close. 23.27? I was going to say, I thought it was closer to like 24 flies, but... It'd be like that sometimes. Found your problem. All right, last problem. We're talking trees. I know. What are we thinking? We about ready? Not yet? Some of us are kind of ready. All right, so we've got all of these wood products, and they can be classified by their lifespan. Short, medium, medium-long, and long. All right, the percentage of the remaining products after T years is given by that equation. So what would be that decay rate? Yeah, so if you remember, I'm going to swing up here for a second. The initial formula is always a negative B. Oh, you stupid thing. It's negative B. So it was a positive number down there, which means B should be negative, where it's decaying. All right, does that kind of make sense? So when you're looking at it, you're still right. It's still the 0.0581. They, in the book, recommend that you take the absolute value of it, which is still going to give you the 5.81% for how much it's decaying. Because this should, like B itself, should be a negative. It's absolute value signs. Yeah. I'll try making them longer. Yes. Carly. Yeah. No matter what. Well, when we take an absolute value of it, it's always going to spit out as positive. So, you were just testing. All right, so how long will it take for this tree population to hit 50? Now, when we go to do this, it's going to be 50 equals 100 point, what was that, 33952. Now, first and third, we're like, okay, I can type that into the calculator. I'm like, all right, have fun. Like, you got Y1, you got Y2, good luck. Like, now you gotta mess with the window, and you gotta try and find everything. You can still solve this algebraically. It's not pretty, but it's doable. Do you guys want to see the work for it? All right. So, let me get us some extra room. All right. Treat it like a proportion. I'm going to multiply that entire denominator up. So now I've got 50 times 100, not 100 yet, times 1 plus 0.0316 E How do you guys want to solve from here? Yeah, divide by 50. Don't distribute. That's going to suck. All right. We're already dealing with hideous numbers. Let's make our lives a little easier. All right. So what is 100 point blah, blah, blah divided by 2? Or divided by 50? Should be 2 point something. 7. 0. All right, now what do I need to do? Yeah, subtract 1. So you guys know in your calculator, once you get that answer, you can just hit -1 and hit enter, and it will take the answer that you just got and make your life a little easier. So point. All right, divide by this. And then I would just jump straight to absolute value, or natural log of all this crap. And then divide it by the decimal. and that should equal T. $59.6. Yeah. So, after 59.6 years, we are down to 50% of those trees. Now, last question I've got for you is why can I have a numerator that's greater than 100? So remember that carrying limit was 100.3 blah, 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 blah. What was it again? 39? So why is it a little bit greater than 100? Yeah. So if I know my maximum amount is 100, I need to make my carrying limit a little bit above 100 so the 100 can fit underneath of it. Does that make sense? Like if I graph it and this is my carrying limit, I need to make sure that the max of 100 is still underneath of it. So they just give me a little bit of wiggle room with the 100.4 so I can hit 100% underneath it. Bueno? We done. Cool.